All right. Hi, Safi. So today we are going to solve some previous year questions on organometallic chemistry. So first, please confirm that you are able to hear my voice properly and see the slide as well. Okay, so let me tell you a bit about myself. My name is Jagriti Sharma and I'm an educator on the Unacademy Plus platform. And guys, Plus platform is basically providing you regular classes, right? It is providing you regular classes for the competitive exams, and I'm specifically teaching for CSIR NET exam. Alright, so I'm teaching for CSIR NET exam, Chemical Sciences. Okay, so if you visit my profile, you will be able to see a number of courses over here, and the courses which I am running right now, I'm taking right now are these. These are my courses: capsule course on inorganic chemistry, crash course on organic chemistry, right? And in the upcoming month of December, I am conducting 3 courses which are like this. First of all, I would like to tell you about the practice course on chemical sciences with MCQ. So in this course over here, I aim to solve 200, or let's say more than 200 MCQs. Alright, and I hope that at this point of your examination, this will be very helpful to you, right? And there is one more course which will be a short trick course. It will be a short trick course for scoring maximum marks in section B. Alright, so there is one more course. So these courses are going to be till 15th of December, before 15th of December, basically before the exam. And guys, after the exam, we are going to talk about the preparation strategy of June 2020. Why is it important? Because see, if we are not talking about the strategy in the very beginning of the session, then you will not be able to make up your mind, right? So it is better to first make up your mind that how we are going to study and then proceed to study itself, right? So that is why we are focusing on a preparation or a strategy course before starting the preparation from January 2020, right? So we will be starting our actual courses from January 2020. Okay, and before that, we want to stress upon having a good strategy and knowing what you are getting yourself into, right? So knowing that also helps you a lot, right? So these are my courses for the month of December. The practice course, MCQ practice course, then there is a course separately for section B, and this is my strategy course, right? So I'm having 3 courses in the month of December. And guys, if you want to join Plus, then what you can do is you can take one of the subscription packages which I will talk about. Also, what you can do is you can just click on special classes over here, and then the upcoming special classes, right? You can just click over here. The upcoming special classes will also show you. So I'm having 7 to 8 free classes. I'm having 7 to 8 special classes in the upcoming month, and you will also be able to see my recorded special classes in the last few months, right? And all of them were focused on previous year questions. So if you want, you can visit them. I hope it will be really beneficial for you. And yes, if you want to join the Plus platform where we are conducting regular classes with doubt solving classes and definitely all the kind of support and quizzes. So you can take one of these subscription package. The 1 month plan is 2100 per month. The 3 month plan is 5250 for 3 months. But basically it is more economical because here per month fee is less. Then we have 6 month plan, 8400. Then we have 12 month plan, 10,500, and 24 month plan, which is 16,800 for 24 months. Okay, so guys, basically we would suggest you to plan according to your exam, right? So if you are preparing, if you are serious about June 2020, then I would suggest you that if you take your subscription now, it should be 6 months or let's say 12 months basically, because then it would be much more beneficial, right? You will have guidance for the December 19 exam as well as for the June 2020 exam, right? And whenever you are subscribing, always use a referral code of the educator, because it is going to give you a 10% discount, guys. And my code is JagritiS. And if you want to subscribe, then do not forget using my code. It is capital J, JagritiS. Okay, and it is going to give you a 10% discount in which of the subscription package you want to have. All right, and yes, all right guys, so now we are going to focus on solving our questions. Okay, so we will focus on solving questions, right? Okay, hello Nazma, hi everyone. Okay, so yes guys, we are going to start solving our questions. So the first question is over here. The first question is over here. The refluxing of, this is our basically it is written as a hydrate salt, like this, simple salt. So this is our complex. Okay, so the refluxing of this rhodium complex with an excess of phosphine in ethanol gives a complex A. Alright, so you have to find out what is the complex A, which is formed by refluxing of rhodium trichloride with an excess of phosphine ligand in ethanol, right? So you have to find complex A. Along with that, you also have to find the valence electron count on the rhodium as well. So you also have to count the valence electron count on the rhodium. So these are the four options which are given to you. So what you can do is you can first of all you can rearrange this molecule like this. Okay, so you can just take the water inside, isn't it? You can take the water inside like this, and then you can write it like this, because there are 3Cl, isn't it? So definitely water would be there in the coordination sphere, isn't it? Right. So if you are proceeding with this question, then it is a very easy question, guys, because see, most of the times whenever we are studying organometallic reactions, right, so we always come across Wilkinson's catalyst. Wilkinson's catalyst. What is a Wilkinson catalyst? It is a organometallic catalyst which basically reduces alkenes to alkanes. Okay, and that also to the terminal, or let's say to our terminal alkene, or let's say less hindered alkene. Yes, so the terminal or the less hindered alkene, it reduces to alkane. This is the work of Wilkinson's catalyst, and it is prepared very simply. It is prepared by taking our rhodium chloride and refluxing it with phosphine in the presence of ethanol. It is a one-step synthesis and it is very easily prepared. So guys, if you know already what is Wilkinson's catalyst and how it is prepared, then you will very easily be able to answer this question. Okay, very easily you will be able to answer this question. All right. Okay, so Yeah, so this is our answer, right? So this is our Wilkinson's catalyst, and now we are just going to count the number of electrons for it. Okay, so we are going to count the number of electrons. How? Very easy. On rhodium we are having 9 electron, 9 valence cell. So basically guys, what I do is I try to calculate by neutral method. Okay, I try to calculate by neutral method, guys. Okay, so by neutral method I'm just taking the valence electrons on the rhodium metal, which is 9, then plus 1 for chlorine, then phosphine. There are 3 phosphine ligands, so 2 into 3, which is basically phosphine is neutral, right? So phosphine is giving 2 electrons. Okay, so it is 2 into 3 for phosphine. So total is 9 plus 1, 10, 2 into 3, 6. So we are having a 16 electron count. Okay, so our Wilkinson's catalyst is having a 16 electron count. Right, so our answer is over here. So we are having both of them 16. But the correct formula is this one, triphenyl phosphine. We are having only 3. So A is our correct answer. Okay, I hope that this was an easy question, and I hope that you were able to do this question. So now we are going to move forward to another question, which is like this. So this question is asking us the beta hydrogen elimination will be facile in. So which of the beta hydrogen elimination will be facile? So guys, as we can see, for this reaction you must have some idea of beta hydrogen elimination. Okay guys, so have you studied about the beta hydrogen elimination? Tell me. Yes, about the beta hydrogen elimination. Yes, everyone. Okay, not getting many responses today. Net slow. Alright, so a beta hydrogen elimination reaction is a very simple reaction, and what we are going to do is we are just going to see the mechanism of a beta hydrogen elimination, right? And then we would be able to tell that in A, B, C and D, from A, B, C and D, which of the following will be very easily will be a very facile reaction. Okay, so first of all, what is beta hydrogen elimination? So this complex over here is very nicely showing that what is a beta hydrogen elimination, right? What is a beta hydrogen elimination? Okay, so as we can see over here that this is our alpha carbon and this is our beta carbon. So whenever we are having beta hydrogens, whenever we are having beta hydrogen in the organometallic compound, then there is a very good possibility of beta hydrogen elimination taking place, right? Sometimes we want the reaction to happen, sometimes we don't want the reaction to happen, right? So what happens is, see over here, if there is a beta hydrogen like this, then the metal is going to just take up the hydrogen and the bond are going to fall over like this. Okay, the bond is going to fall on the alkene, and the metal is basically the bond which is falling over here. The metal is actually taking up the H plus, right? So the metal has taken the H, and the double bond, basically the alkene system, has separated like this. Okay, so still the alkene is bonded, but it is not bonded to the hydrogen anymore, right? So there was beta hydrogen elimination from the alkene system. Okay, all right, so basically this reaction is favorable in this first case, because over here both the carbons are sp3 carbons, isn't it? Both of them are sp3 carbons, right? So this elimination is possible. Now, if we talk about the other options, first of all, if we look at this option in which the metal and hydrogens are far apart from each other, they are very far, definitely it is not happening. And even if the elimination happens, then where would the sigma bond go, because it is already triple bond, right? So definitely not happening in this case. Then in this case over here, what we can see is the hydrogen can be extracted and the double bond can become a triple bond, but it is not as stable as basically it is not as facile as the one in which the bonds are removed from the sp3 carbons, right? It is not as facile. Similarly, if we see the products of this reaction, then the hydrogen which is removed from here like this, then what can happen, this is what is produced. So basically an alene system is produced, and it is also not very facile. So the whenever an alene or an alkyne system is being produced, we are not going to say that this is going to be a very facile process, because it is not very commonly observed. The most commonly observed beta hydrogen elimination is our simple reaction like this. Okay, so that is why we can say the most facile reaction, beta hydrogen elimination, is going to happen in option number A. All right guys, I hope this was easy. It was very very easy, I hope. Okay, so we are having one more question. The question is asking, amongst the following, we are having four complexes. The compounds with most shielded and de-shielded cyclopentadienyl protons respectively are. So which are the most shielded? What are shielded, guys? Basically, this is our cyclopentadienyl anion. Okay, so they are our cyclopentadiene system. All right. So what happens is, we are having 5 hydrogens like this. Okay, so now it depends upon how much electron rich is the cyclopentadienyl system. The richer the cyclopentadienyl system, the more shielded will be our protons. Okay, and if the electron density is taken out from the cyclopentadienyl anion, then the hydrogens will be more de-shielded. Okay, so this is what the question is asking. So the question is basically asking that who is going to take away the electron density from Cp and who is going to give it electron density. Alright, so that is what the question is asking, and these are our answers, options basically A, B, C and D. Okay, so we are going to see the structure of these complexes one by one. Let's see. Okay, so basically what we have over here is this, something like this. So basically in the first complex, what we see is that, just a second, let me see the options again. Okay, all right guys, so yes, these are the options. So what we see over here is that if we are having manganese and cyclopentadienyl like this, okay, N5 contributing electron from all the 5 carbons basically. Okay, so if I'm having a complex like this, then I can see there are, on one side there is this cyclopentadienyl anion ligand. On the other side of manganese, there are carboxylic, carbonyl group basically. So we know that carbon monoxide, when it is attached as a ligand, it is also a very good sigma donor as well as a very good pi acceptor. Yes, it is having vacant pi star orbitals. It is also called pi acid ligand. That is why it is also called pi acid ligand, right? So it is a very good pi accepting ligand. So over here, if the cyclopentadienyl, basically if the Cp is giving electrons to the manganese, if it is giving electrons to manganese, then manganese will be very nicely able to disperse its charge onto the carbonyls, because the carbonyls can take up the charge, right? So this is why the this CP becomes very electron deficient, we can say. Electron deficient, we can say. Why? Because of the presence of carbonyls on the opposite side, because the CP is giving to manganese and manganese is dispersing it to carbonyls, okay, by pi back bonding. Yes, we have studied about pi back bonding. Yes, so because of the presence of 3 carbonyl groups, this compound has the most de-shielded protons. This has the most de-shielded protons. And how do I know it is the most de-shielded? Because in the other complexes they are simple ferrocene, okay, and ruthenosine and osmiocene, like this. So in these complexes I'm not having a carbonyl ligand, okay. So they are simple ferrocenes over here. Now if I am comparing the 3 systems over here, then I can see that the size of the central metal atom is increasing. Yes, the size of the central metal atom is increasing. And what does that mean? That means that the electron density is decreasing as the size increases. Yes, so if the electron density is decreasing as the size increases, then also what will happen? Then also the CP will try to push electrons towards the metal. Yes, if the electron density is decreasing, the ligand will try to push the electrons toward metal. However, in the case of iron, it is the smallest and it is the most electron dense. It is the most electron dense as compared to the other 2 systems, right? So that is why we can say that the CP over here is also it is also not made electron deficient, right? So these protons are going to be the most shielded. These protons are going to be the most shielded, and the one with manganese, because of the carbonyl group, it will be the most de-shielded, guys, okay. Alright, so our answer must say that these are shielded and the first one are de-shielded. Alright, so it is there in which option? Most shielded 4 and de-shielded 1. So 4 and 1, option number A is correct. Alright, I hope that you got this. It is a very easy concept, guys. We just have to look for the size and the charge, okay. Alright, okay, so we are having one more good question. From the same exam, June 2015. So the least probable product from A on reductive elimination is. So the question is asking us which is the least probable, which means which one is having the least possibility of formation, which will not form basically. Alright, on the reductive elimination of A. So basically we are talking about only reductive elimination reaction, okay. We are talking about reductive elimination reaction, and these are our options, okay, and these are our options. Okay, so I would suggest you to take a pause and think about it yourself, right? Think about the options, guys. I'm not able to see your comments today. I don't know why, but I'm not able to see any of your comments today. I hope I was able to, but I don't know. Okay, so try this reaction by yourself once, okay, and yeah, so okay, so if the reductive elimination takes place, let me just tell you, okay, so if the reductive elimination takes place, then the molecule is going to, these 2 fragments are going to connect together and they are going to leave the metal, isn't it? So they are going to leave the metal will be like this, and they're going to leave the metal and they're just going to form this possibility. This molecule, basically they have formed N-butane. Yes, so N-butane is the most probable. It is not least probable, it is the most probable, isn't it? It is the most probable. So we just can't tick off option number A, right? So what we have to do is we have to see for least probable. So we can just cross option A because it is most probable, right? We can directly see there is a very good probability. Okay, what about these other three options? Let us quickly see. So guys, as the question is definitely asking about reductive elimination. So in the first step, what we did was we just connected the CH3 group as well as this propane chain, and this is our butane which was formed. Okay, so this is one possibility that we had discussed. What is the other possibility? So guys, the other possibility can, can be a variety of reactions. Okay, so what I did over here is like this. So basically we are having a hydrogen over here, isn't it? We are having a hydrogen over here. So I can just do the alpha migratory elimination and I can just bring the hydrogen back to the metal. And no, it is beta migratory elimination. Yes, alpha and beta, right? So I can just bring back the hydrogen to the metal, and yes, it is this hydrogen, right? Yes, so it is this hydrogen which I can bring back to the metal. And now what are the possibilities that I'm having that I have to see? So one of the possibilities is that now the H and the CH3, both the methyl group and the H, are now cis to each other. And this is the criteria that for reductive elimination we require two cis groups. So now it can give us a methane, isn't it? After the reductive elimination, it can give us a methane, and the fragment which is kept with the metal is our alkene basically. Okay, so this is one possibility. What is the other possibility? Let's say for example the CH3 and this group, the alkene, are cis to each other. Now obviously it is not and we can't see that it is cis, but let's say the conformation is changing and so on. Then this CH3 and this alkene are cis to each other, let's say. Then they are going to give reductive elimination and they are going to form an alkene like this. Okay, so these are the two fragments which have joined together, right guys? So this type of product is least probable, we can say. Why least probable? Because the sp3 carbon is much more facile, or let's say much more nicely giving the reductive elimination. This is our alkene system, sp2 carbon. So our alkene is not as nicely giving reductive elimination, rather it will give some other type of reaction but not directly reductive elimination to form an alkene like this. Okay, so we don't see much of reductive elimination in alkenes, right? And that is why we can say that this is not one of a very good possibility. What is the other possibility? We have one more option, right? The other possibility is that, let me just show it to you. The other possibility is that if I have just twisted this molecule basically, or let's say I have just made the metal bond like this, because there is one hydrogen. Alright, so I have made the metal and hydrogen bond like this. Okay, this is our CH3. So now the hydrogen can add over, or let's say the hydrogen adds over to this carbon, and the metal, let's ignore this. So the hydrogen adds to the terminal carbon, okay, which is not usually the case because the metal wants to stay away and at the least hindered carbon. Okay, but let's say there is one possibility that the hydrogen adds to over this carbon terminal one. Then the metal is left out with this one. Then the metal is left out with this carbon, branched carbon, right? Now there is a possibility of reductive elimination of these two groups, and still this type of a compound is still possible, and it is also there in the options. So we can say this is also possible, methane is also possible, butane is also possible, just that our 2-butene is Not possible, because alkenes don't much give reductive elimination. So answer is option number C. Okay guys, I hope that you were able to understand this. I hope that you have given the answer before me, that would be even better. All right, okay, so let's see one more question. Okay, so yes, this question is asking with respect to sigma and pi bonding in the platinum and alkyne group in the structure given below, which of the following represents the correct bonding? Okay, so this is basically our alkyne and this is the platinum, and there is a perpendicular bond, and we can understand what this bond is basically. Yes, so we know what this bond is basically. So what we have to do, we just have to answer the question and we have to find out the perfect interaction, right? The perfect interaction. Okay, so guys, we know about how some alkenes and some alkynes, how some carbon carbon double bond and carbon carbon triple bond are able to donate their pi density to the metal, isn't it? How they are able to donate the pi density, pi electron density to the metal. So for the alkene or the alkyne, they are donating the pi electron density, but for metal it enters into the metal sigma orbital. So for the metal it is a sigma bond only. Okay, but for the alkene or alkyne system it is a pi bond. Yes, so this is one interaction. The second interaction which is possible between such compounds is that metal can, when it becomes electron rich and the electrons are in excess, so the metal can, give back the excess electron density by pi back donation. Yes, by pi back donation. And what are the orbitals required for pi back donation? The orbitals definitely are the metal pi into the ligand pi star. Yes, the metal pi into the ligand pi star, because the ligand over here is our pi acid ligand. Yes, it is a pi acid ligand because it has a vacant pi star orbital. So it can take up the electron density back from the metal into the pi star orbital. Right? So that is why we just have to tick off the correct pi and basically the correct interaction. Okay. So the first one will be a sigma bond. The first one will be a sigma bond, okay, which is formed by the ligand pi orbitals giving electron density into the metal sigma orbitals. Okay, and the second interaction would be that the metal is now donating from the pi orbitals into the ligand's pi star orbital. Okay, so these should be the interactions, right? And do we have them in the options? A is having metal sigma, no. Ligand sigma to metal pi, no. Ligand pi to metal pi, no, it is ligand pi to metal sigma. So here it is ligand pi to metal sigma. Let's see, this is looks like correct. And the second one is metal pi to ligand pi star. Definitely this is our pi back bonding. So answer is option number D. Okay, and even if you want to see the interactions, then I have shown it for you over here. Okay, so first of all, the ligand which we are having, it is having pi electrons like this. So this is the pi the ligand is donating from the filled pi orbitals. Okay, and it is donating into the empty metal d orbitals, right? So this looks like a sigma donation for the metal. Okay, but what happens is when there is a pi back donation, then what happens is the metal from pi gives to ligand pi star. So definitely the geometry should be same. So the metal pi are basically the d orbitals only, the dxy, dyz, dzx, t2g, right? So the symmetry of the metal dxy is similar to the pi star orbital of the alkene. Okay, so this is how the back donation can also take place. Alright guys, so this is our pi donation back to the ligand. Okay, so these are the interactions which are leading to the formation of the complex which is given in the question. Right, I hope that this was clear to you. Yes, because guys, I can't see your comments. I can't see the live chat right now. I don't know. It is not coming. Right. So I hope that these are all clear to you. Then we have one more very good question. Then we have one more very good question from June 2015, guys, and it is an evergreen question, right? So it is an evergreen question. So if you have not yet heard about the names of these reactions, I would suggest you to learn it by heart, because these questions are evergreen. Either they will be asked in organometallic chemistry, or they will be asked in organic chemistry, right? Or they can, most of the times they are always asked in organic chemistry. So definitely you have to know these reactions. Okay, so over here these are the coupling reactions. So match column A with the coupling reactions with column B over here like this. Okay, so we are given Suzuki coupling, Heck coupling, Sonogashira coupling and Neghishi coupling. Okay, and we have to match them with correct reagent. Okay, we have to do that. We have to match them with the correct reagent. So guys, first of all, not just directly telling you the correct answer. First of all, see, yesterday also we had talked about palladium catalyzed reactions. We had also talked about palladium catalyzed reactions, and there are umpteen reactions of palladium. You will get tired, but palladium won't get tired. Okay, so there are a lot of reactions of palladium. Okay, so let's start from Suzuki coupling. Okay, so whenever we are having Suzuki coupling, there must be a borate. Okay, so alkylyl borate like this, and whenever it is the transmetallation step, there is a transmetallation step between palladium and boron, right? So in which the boron is transferring this whole group to the palladium and so on. Yesterday only we talked about this. Okay, so whenever we are having boron in the system, it is our Suzuki coupling. Okay, so yes guys, let me tell you one thing. So this question is a very easy question, because here you don't have to tell the whole mechanism. You just have to tell the name of the reaction and the reagent. Okay, so what you can do is, if for this exam, if you are not able to learn everything about Suzuki coupling or palladium catalyzed reactions, at least learn the name of the reaction and the reagent, at least, so that if a match the following question is asked, you will be able to answer it. Okay, so this is our Suzuki coupling, in which a boron complex is used like this. Similarly, we are having Stille coupling. So in Stille coupling, we are using tin. So I remember it like this: S for Stille and SN for tin. I remember it like this. Okay, so in the Stille coupling, we are using a tin complex basically, and the tin is again going to do the transmetallation to the palladium, and palladium is going to join both the fragments that we want to join. Okay, so this is Stille coupling. Similarly, in the Heck reaction, we are again using palladium in the presence of phosphine and ethylene triamine as a base, and over here, as we can see, it is our alpha beta unsaturated. Over here it looks like our acetal, although okay, so this is ester. Yeah, so this is our alpha beta unsaturated ester. Okay, so this is what we are having in the Heck reaction. Okay, so Neghishi coupling is also there. So in the Neghishi coupling, we are using zinc for transmetallation, and palladium is always there, right? So we are using zinc in the Neghishi coupling, and again there will be these two alkene system will be joined together, right? So if you have started with over here, so this alkynyl bromide, this group will be removed, and directly over here from transmetallation and so many steps we had discussed yesterday. So after doing so many steps, this directly will be joined over here. So there will be a direct joint between this carbon and this carbon, as we can see over here. Okay, so this is again Neghishi coupling. Similarly, we are having Miura coupling, but it is not asked in the question, so we can just move further to Sonogashira coupling. So in the Sonogashira coupling, as we can see, what is used? Definitely palladium, phosphine is used, and the alkynyl system is used. Basically we are using the alkynes. We are joining our carbon Br, we are breaking this carbon Br bond and we are joining over here to the alkyne system, triple bond. So we are using triple bonds in the Sonogashira coupling. Alright, so I hope that by now you must have some idea about the reaction, and let's see the question right now. So what are the options? So we are having an ester, an alpha beta unsaturated ester over here. So we are having an alpha beta unsaturated ester over here, and guys, just now we saw that in the Heck reaction, in the Heck coupling, we are using alpha beta unsaturated ester. Okay, then in the Sonogashira reaction we just saw that we are using alkyne system, isn't it? We are using the alkyne system in Sonogashira reaction. Similarly, in the Neghishi coupling we saw we are using zinc. Okay, so we are using our zinc salt, and definitely this is our so this is our group that we want to do transmetallation with the palladium, right? So basically what we have to look for some key reagents, and then we'll be able to match very easily. And our Suzuki coupling was on the top, and it definitely uses the borate. Okay, so this is our final answer. So A is connected with 2, B is connected with 1, A is connected with 2, B is connected with 1, C is connected with 4, and D with 3. C 4 and D 3. So answer is option number A. So I did not give you option number A. So this is the first one is option number A, and it is our correct answer. Alright. So these reactions are evergreen, guys. Definitely try to study them a little bit, and they are going to help you in the CSIR exam definitely. Okay. So let's now see one more thing, one more question, that the aqueous chromium 2 plus affects 1 electron reduction of this compound. So it is carrying out 1 electron reduction of this complex over here. This is a cobalt complex giving compound Y. Okay, now compound Y undergoes rapid hydrolysis. What do we mean by rapid hydrolysis, guys? We mean that Y has become labile, isn't it? Because it is giving rapid hydrolysis, so Y must be labile. Yes, A, B, C and D. So these are our options. So guys, in the plus course we had talked about the inner sphere mechanism, right? The inner sphere electron reduction mechanism and the outer sphere electron reduction mechanism. Okay, so in the inner sphere electron transfer mechanism, sorry. Okay, so it is basically like one electron transfer mechanism. So what happens is ultimately reduction of one and the oxidation of the other is going to happen, redox reaction, right? So what happens in the inner sphere is that there was a ligand which was able to form a bridge between the two complexes, right? So can we see a ligand which forms a bridge basically? So we are given only one complex over here, and in that complex I can see chlorine, and chlorine forms a very good bridge between two complexes, right? And it is the inner sphere mechanism is very efficient with such ligands. Okay, so if we are talking about the inner sphere mechanism, then we must know that after the electron transfer, let's say along with the electron transfer, there is one atom or group transfer as well. So who is that atom or the group which is getting transferred? We can see that in the mechanism. Okay, so yeah, so we are having the aqueous chromium complex. So basically we are having aqueous chromium complex like this. So this is one of our complexes, and the other complex is over here, pentaamine chloro complex of cobalt, right? So this is what we are having, something like this, 2 plus. Okay, so which is basically this 2 plus is the cobalt is there in +3 oxidation state because there is a chlorine -1 also. So the total charge on the total oxidation state of cobalt will be +3, and for chromium it is +2 only. So definitely chromium is going to give one electron to cobalt, right? So chromium will become chromium 3+. Alright, so let us see the whole mechanism. Alright, so guys, if we are talking about this complex over here, if we are talking about the cobalt complex, so if cobalt is in the +3 oxidation state, then it is our 3d6 system, and because we are having amine as the complex, it will be low spin, and low spin 3d6 is very stable because of high stabilization crystal field stabilization energy, and that is why it becomes inert. Okay, what about the chromium complex? Let's see the chromium complex. It is 2+, so chromium 2+ is D4 system. It is 3D4 system. Alright, and D4 system, that also high spin, so definitely it is labile. Okay, so definitely it is labile. Now what happens is, the question is asking that after the electron reduction, the cobalt complex becomes labile. Okay, basically, so what is the complex form that we have to see? We have to tell the the formula of the complex, which is very easy, guys. See what happens in the inner sphere mechanism. What happens in the inner sphere electron transfer mechanism? One of the group is going to become the bridging ligand. Let's say the Cl becomes the bridging ligand over here, so definitely one of the ligand has to remove. So one water molecule removes from the labile complex. Because it is labile, it can easily lose it, right? So one of the water molecule is removed, and there is a chlorine bridge over here like this. So there is a chlorine bridge over here, right? Now definitely the chromium, which was +2, now definitely it can give one electron to cobalt through the bridge, right? Through the bridge. Okay, and after doing that, after that has happened, after the electron transfer has happened, right, after the electron transfer has happened, the Cl is going to remain with the one who has a greater charge, right? So after the electron transfer has happened, chromium becomes chromium 3+. From chromium, it was chromium 2+, and it becomes chromium 3+. So the chlorine now stays with chromium. Okay, and this is our complex that we are having. So this is one complex in which chromium becomes chromium 3+, and chromium 3+ is our D3 system. And guys, D3 system is again high CFSE. Okay, so it is again inert. Alright, then what is the other thing that happened? The other part of the complex is this one: cobalt became cobalt 2+ in the presence of ammonia, right? And it became D7 system, right? And that is why it becomes labile, because the crystal field stabilization energy has decreased, and definitely it is undergoing rapid hydrolysis because now it has become labile. Okay, so this is our complex, which after reduction has formed cobalt pentaamine complex. So this is our complex, guys: cobalt pentaamine complex, cobalt 2+. Alright, at first cobalt was there in +3, 2 for 2+ to already there, and +1 for chlorine also, so it was +3 before. Now after reduction became 2+, right? And it undergoes rapid hydrolysis also. Okay, so answer is option number A. Okay, it is a very simple question, guys. The inner sphere mechanism, we just have to know it, so that we are not confused between all these other options. We just have to know it, right? And in the option number D, we can see chromium is there in +3 oxidation state, and definitely the D3 system is inert because it is having high CFSE value, isn't it? So that is why it will turn inert. Okay, alright guys, so I hope that this question was clear to you. And let me once again tell you that my name is Jagriti Sharma, and I'm an educator on the Unacademy Plus platform. And I would suggest you to go and watch all my free courses. Okay, and also in the month of December, I have started 3+ courses. So in the 3+ courses, the first one is basically 200 to 250 practice MCQ course in which we are just going to practice so many MCQs right before the exam, and the other course is focused on the solving question from section B. So the other course is focused on the tips and tricks of section B question solving, right? Then I am also having after the exam from 18th of December, I am going to start a strategy course. I'm also starting a strategy course for the preparation of June 2020. So guys, I can't emphasize how important it is to start preparing the strategy before actually studying, okay? Because definitely that is the only thing that helps you. The strategy is going to keep you on your track, okay? So that is why we have to know how to prepare a strategy, okay? So guys, if you have seen my content and if you like my content, then you can join me on the Plus platform, where we are all having live and structured classes with all the weekly quizzes and doubt clearing classes. Also, there are a lot of other top educators who are definitely preparing great content to help you guys. So yes, my name is Jagriti Sharma again, and this is my code guys, JagritiS. So it is J capital and S capital, and using this code for any Plus subscription is going to give you a 10% discount, okay? All right guys, so thank you so much for watching, and tomorrow also I will see you on the same time, 8 p.m. Tomorrow also I'm going to see you on the same time, and we are going to solve previous year questions on organic spectroscopy, which is my favorite, organic spectroscopy. All right guys, okay then, see you tomorrow, and if you plan to take the subscription, don't forget to use my code, okay? Thank you so much guys.